Hello, am I audible, guys? Today I'll be discussing Boot Chef Starters 193. Starters from 90. Okay, so let's start. 195, sorry. So let's start with the discussion. The first problem was marble collector. So there are a total of m possible types of marbles that you want to collect. They are unnumbered, 1 to 11. You currently have n marbles with you with type A1, A2 till AN. Note that you may have the same type of marble twice or more. Find the number of types of marble that you still have not collected. Okay. And the constraints are n and m are less than 100. T is less than 100. So n square, I think, can pass. N square or maybe even n. So basically, the question is like this. We have n marbles, m marbles, m types of marbles, right? And m we are given less than equal to 100. And then we have n different marbles of type A1, A2, AN, and we need to find the number of types of marble that we do not have. So let's see the test cases. First test case is 3, 3 and 1, 1, 2. So 3, 3, 1, 1, 2. So 3 is the number of marbles that we have, and this 3 is the total number of different types of marbles. So there are 1, 2, and 3. These are the types of marbles that are there, and we only have 1 and 2. We can see that we only have 1 and 2. So we don't have 3. Hence the answer would be 1. Since we need to find the number of types of marbles that we don't have. So answer would be 1. And in the next test case, we have 100, then 40. So we have one marble of number 42, and there are 100 types of marbles. So the only type that we have is 42. So our answer would be 99. Since we don't have 1, 2 till 41 and then 43 till 100. And for test case 3, 3, 1 and 1, 1, 1. So we have 3 marbles of types 1, 1, 1, and there is only one type of marble. And since there is only one type of marble and we already have it, so answer would be 0. So since the constraints are like this, since m is less than equal to 100, what we can do is just maintain a bool array of size m plus 1, and whatever types of marbles that we get, whatever types of marble that we get, we can just uh, array of that type of marble as true. Set initially to false. Set all to false initially. So as we get the marbles, we mark them true in the Boolean array of size m plus 1. And after we mark all the marbles that we have, then the indices of array with false value would be the answer. Count of indices of array with false value would be the answer. So basically, I'll just try run on this test case. So let's create the Boolean array of 3 size. This would be basically 1, 2, and 3. This would be false, initially false, false. And then we get 1, 1, 2 as our marbles. So 1, 1, 2. So when 1 comes, we mark this as true. Then again 1 comes, since this we again mark this as true, it doesn't change anything. And when 2 comes, we mark this as true. And in the end, since there is only one false, then our answer would be true. So the time complexity would be O of m plus n, since O of m for declaring the m-sized array and O of n for processing the n types and n marbles that we have. I'll show you guys the code. So basically, this is the Boolean array of m plus 1 size. And then I take input the marbles that I have and mark them true. And in the end, I check for each marble from 1 to m. If it is not found yet, then I increase the answer and see how it comes. So, does anyone have any doubts in this question? Oh, I think it's clear for everyone. Let's move on to the next question. This is problem B, string deletions. So you are given a binary string S of size n and can perform the following operation on it. Pick 3 integers I, j, k such that uh, they need to be distinct and in increasing order. I should be less than j and j should be less than k. And Si should not be equal to Sj and Sj should not be equal to Sk. Then delete Sj from the string concatenating the parts form. Okay. Find the minimum possible length of the string after performing some number of operations on it. And the constraints are n is less than 2e5 and sum of n over all test cases does not exceed 2e5. So expected time complexity would be O of n or O of n log n. So I'll just explain the problem. Problem B. So basically we are given a binary string S, and we can perform operations on it. In one operation, what we can do, we can choose 3 indices I, j, k like this, and they also should be less than 1 and size of S. So we choose 3 indices I, j, k like this, and also Si is not equal to Sj and Sj is not equal to Sk. And then we remove Sj from the string. So basically our new string becomes S1, S2 till Sj minus 1, then Sj plus 1 till Sk. Also, S1, Si belongs to 0 and 1. So basically one thing we can point out from this property right away is that since Si is not equal to Sj, that must mean Sj must be the opposite of Si. If Si is 1, Sj must be 0. If Si is 0, Sj must be 1. So if Si is 0, then Sj must be 1. And if Si is 1, then Sj must be 0. Also, since Sj is not equal to Sk, then if Sj is 1, Sk must be 0. And if Sj is 0, Sk must be 1. So I can pick 3 indices like this only. Like they should be 0, 1, 0 or 1, 0. So Si, Sj, Sk should be of this form only. So let's see the test cases. The first test case is 101. So obviously what we can do is choose 3 indices since there are only 3 indices, so we'll choose them. And this 0 will be removed. So the final string would be this, and for each test case, print the minimum final length. So the minimum final length will be 2. Then the next test case is 3 100. And since we can't pick any 3 indices of the form 0 1 0 or 1 0 1, So we can't perform any operations on this. So again, this would be 0, I mean 3, since we cannot perform any operations, the length will be 3. Then we have 4, 1, 0, 1, 0. 4, 1, 0, 1, 0. Now I can perform two operations right here in this case. What I can do is I can maybe choose 1, 0, 1 and delete this 0, or I can choose 0, 1, 0 and delete this one. Let's try both of these and see what happens. So let's first try this operation. So the string would become 1, 1, 0, and then I cannot perform any operations further. So in this case, the answer would be 3. And if I perform this operation, then the string would become 1, 0, 0, and again in this case, the answer would be 3. So overall, the answer would be again 3. Right. So this was for the test case part. One thing we can see from this test case is that if the string is of the form like this 1 1 1 1 0 0 0 0, or it is of the form 0 0 0 0 1 1 1 1, then we cannot perform any operations. Cannot perform any operations. So answer in these cases would be just simply n. And another thing, so this would be one observation. This would be one observation. And another thing is that we can pick SI, SJ, and SK, and we'll have to remove SK. So basically, we pick SI, SJ, and SK, and we will remove SJ, and we are also given this 1I, J, K. So sorry, and this is SC. So basically, since I is greater than equal to 1 and J is strictly greater than I, so J must be strictly greater than 1, and similarly J must be strictly greater than size of S. So basically I can never delete the first two elements, first and the last elements. Since the element J is deleted in each operation and J must be greater than 1 and must be less than size of S, I can never delete the first and last element in S. This will be our second observation. Now let's try to figure some stuff out from this observation. So since we cannot delete the first and the last elements, let's see what happens when we fix the first and the last elements. So let's see. So let's say that the given string we have starts with a 0 and ends with a 0, and there are certain elements in between. So in this case, since we have these two zeros at the first and the last elements, so all Sj which are 1 can be deleted using these two zeros. Can be deleted using these two zeros. Okay, and let's mention that case 1, first and last elements are. So basically, I'll show a quick example for this thing. Let's take some example. This one. Okay, so what I said was that I can remove every single one in between in the string if the first and the last are zeros. So how can I do that? In first operation, I'll pick these three indices, and then the string will become 0, 1, 0, 0, 1, 0, 1, 0. Then I'll pick these three indices, and the string will become 0, 0, 0, 1, 0, 1, 0. Then I can pick these three, and then the string will become 0, 0, 0, and similarly, I can pick these three. So So that's how I can remove every single one, because every single one would be obviously between the first and the last element. So I can remove them all. So since now, this is another observation that I made. So since now I can remove every single one. Basically, now I'll have to try to focus on removing at most as many zeros as possible. And now I need to remove as many zeros as possible, which I can do by basically finding the first one and the last one. I can find the first occurrence of one and the last occurrence of one. And what I can do is basically again just like how I did with these two zeros, I can now do with these two ones. And I can now remove every single zero in between. So I can remove this, I can remove this, I can remove this. And then using these two zeros, I can remove this one, this one, this one, and this one. So that's what we can do in this when the first and the last element is zero. So basically, let's take some example again for this case. Let's say the first and last element is zero. Then there are some zeros here, and then basically 0, 0, 0, 1, and then a heaps of zeros. So these three zeros can never be removed because there is no one here. There is no one here. So these three zeros can never be removed, and similarly, these four zeros can never be removed. So these four zeros can never be removed because there is no one here. And using these two zeros, I can remove every single one in between. And what else I can do? Using these two ones, I can remove every single zero that is in between. So basically, I can remove this whole string from the first occurrence of one and till the last occurrence of one. I can always remove this whole string. Since from the first and last occurrence of one, I can remove every single zero in between using these. I can remove every single zero in between the first and the last one. Right. So I find the first one and I find the last one, and then I can remove every single zero in between. And then I can remove every single one from the string. Then I can remove every single one from the string. And after performing these two operations, I'll be left with only these and these zeros, which we proved that cannot be removed from the array. I only remain with some zeros, which we proved cannot be removed from the array, from the string. So basically, our string cannot get any smaller than this because any more zeros cannot be removed from the string, and the only numbers remaining in the string are which cannot be removed. So our string cannot be reduced further. Can never be reduced further. Hence, in this case, our optimal answer would be just the number of zeros in the front plus the number of zeros in the back. So answer would be number of zeros in front plus the number of zeros in the back. for case 1. So that was our case 1. Now let's figure out case 2. So case 2, let's take the exact symmetrical case of this where the first and the last elements are 1. So now easily I can see that from these two ones, similarly I can remove any 0 in between. I can remove all zeros. So since now I can remove all zeros, what I'll do is I'll try to maximize the number of ones that were removed. So the maximum number of ones that can be removed would be between the first occurrence of 0 and the last occurrence of 0. So basically the string must look like this. And again, similarly, what I can do is using these two zeros, I can remove every single one from here. Remove all ones from here. And then I can remove every single 0 from here. So the only things in the end I would be left with will be this and this, which are obviously impossible to left with this, which is impossible to reduce further, because obviously I do not have any zeros here and any zeros here. So these ones can never be removed, since there is no, for these there is no SK that is 0, and for these there is no SI that is 0. So again, for case 2, the answer would be number of ones in the beginning, in the front, plus number of ones in the end. So that would be our answer for case 2. Please. Now let's move on to the next case. Case 3. Case 3 would be, let's take starting with 0 and starting with 1 and ending with 0. So, and also let's mark the first 0 and the last one. That will help us. So basically, if this is the first 0, then these all must be ones. And if this is the last one, then these all must be 0. So from the previous cases, I can immediately tell that using these two ones, what I can do is, okay, first let's mark the ones which cannot be removed. So I cannot remove these, I cannot remove these. Can't be removed. Can't be removed. So the minimum answer that we can have would be 7. Minimum answer is this. These cannot be removed. And using this one and this one, what I can do is remove all zeros in between this. Remove all zeros between this. And using this 0 and this 0, what I can do is remove all ones between this. But there is a problem. I cannot remove every single number between them, because since I require this 0, to remove the zeros in between this. To remove the ones which are present here. I require the zeros to remove those ones. So if I perform this operation first and remove every single 0 in between this, including this one, then I won't be able to remove these ones. Basically, this one cannot be removed now. Let me take an example. So 1 1 1 1 0 and then 1 0 0 0. Let's take some 1 0 0 1 1 0 1 4. So what I can do is let's just pick these 0 and pick this 0 for now and remove all the ones in between. So these are unremovable and these are also unremovable. Let's try to remove all in between. Okay. So let's pick these two zeros and remove every single one in between. So what will happen? I'll get this array 0 0 0 0 and then 3 zeros. So these were the ones that I couldn't remove, and these also are the ones that we can't remove. So basically now I've got 4 leftover zeros now in between, because we have these zeros and now we are unable to remove them because we were able to remove them because of this one, and since we performed operations using these two zeros and removed this one, now we'll not be able to remove these zeros. Basically these zeros are dependent if there is a 1 here or not. So what we can do is we can take another strategy and we can remove every single one except this. That way we'll be left with this one, and using this one and this one, we can remove all the zeros in between. So let's do that. Using this 0, I'll remove these 3 ones. So what I'll get is 1 1 1 1, then a 0 0 0 0, 0 0 0 0, and then this one, and then again 3 zeros. So these 3 were unremovable and these 3 were unremovable. And now what I can do is use these two ones and remove all these zeros. So now I'll be left with this. And these were not removable, and also now I cannot remove this no matter what I do, because even if I had performed the operation using these ones first, then I would have to remove all zeros, and I'll have to leave 1 0 so that I can remove these ones. So I'll always have to leave at least one element in between these. In between these two non-removable sets of elements, I'll always have to leave one element that I cannot remove. So basically, answer in this case would be number of ones in beginning in front plus number of zeros in back and plus 1. So this will be the answer of case 3. And now let's figure out the case 4, which is symmetrical to this case. And the answer would also be quite same. So case 4. So basically now the first element is 0 and the last element is 1. We take the opposite, right? Yes. So let's find out the positions of first 1 and the last 0. So these guys must be zeros and these must be ones. So again, these would be non-removable and these would be non-removable. And then what I can do, I can use this one and this one to remove all the zeros in between here. I'll leave this 1 0 out. I remove all zeros from here. And then since I left this 1 0, what I can do is I can use these two zeros to remove all the ones from it. Remove all ones from it. And in the end, I'll have this one extra element which cannot be. So again, the answer in this case will be number of zeros in the beginning, the start, plus the number of ones in the end. plus 1. This would be answer for case 4. So that was the solution for this question. And since all the counting can be done in just 2 of n, so the answer would be no of n. Also, one thing that I would like to show you guys is instead of solving 4 different cases, we can actually solve this in just 2 cases only. What we can do is just if the see in case number 3 we had the first element as 1, and in case number 4 we had the first element as 0. But in both of the cases, what the answer was, basically the number of elements same in the starting and number of elements same in the ending. That plus 1, that was the answer for both the cases. So what I can do is I can identify if the first element is 1, what I can do is I can just flip all the elements of the array. And now if I had this array, I'll get this array then 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, and then 1, 1, 1. So basically now again the answer would be same because these 3 elements and these 3 elements would be counted in the answer plus 1. So what I can do is I can just flip all the elements and just follow the procedure for case 4. That way I do not have to check for case 3 separate. And similarly, what we can do in case 1 and case 2, we can just, if the first element is 1, we can again just flip all the elements and now it becomes 0, 0, 0, 1, 1 and 0, 0, 0, 0. And again, the answer would be same in both the cases. It would just be the sum of these zeros and these zeros. So that way, we don't have to solve 4 different cases. We just need 2 different cases. So that was it. I'll show you guys the code. So for code, here, if the first element is 1, we just flip all the elements. If it is 0, we can make it 1, and if it is 1, we just make it 0. That is making the first element 0. Now, since we have the first element as 0, if the last element is also 0, then it is case 1. Since first and last element are both 0. Case 1. First and last elements are both 0. So the answer in this case would be the number of zeros in the front and number of zeros in the back. So what we can do is just basically make 2 pointers L and R and just increase the count of L if S of L is 0 and increase the counter of R, decrease the counter of R if S of R is 0. Basically, we put the pointer L here, and if this is 0, we move, and if since again this is 0, we move, again this is 0, we move, and this is 1, so we stop. We put the pointer R here, again it is 0, we move, we move, we move, we move, and since this is 1, we stop here. So the number of zeros in the front would be L simply in 0-based indexing because 0, 1, 2, 3. So 3 would be the number of zeros in beginning. And since this is n minus 1, n minus 2, n minus 3, n minus 4, and n minus 5. So what we can do is basically n minus r, that would be 5 and reduce 1. So n minus r minus 1 and that would be the number of zeros in beginning and number of zeros in front. And this is the case that we identified earlier. Basically this case. So if L points to this and R points to this, basically since now if L is greater than or equal to R, so this was L less than equal to R. Basically L and R cannot be same because they must be pointing to different. Okay. So, sorry. If when I try to find the first one from the L, what I can do is I'll get my pointer to here, and since R is not 0, I'll have my pointer here. So basically, just a second. Okay, sorry. This is the case where the last element is 0. So, sorry, we'll have to check this one in the next one because currently we are checking for when the first and last elements are 0. So when the first and last elements are 0, if I don't think this, no, this cannot be hit. So this will only be hit when there is a case like this, 0, 0, 0, 0, 0, 0, 0. So L and R, what will happen is basically L will completely move to this end and R will move to this end. So now L will become greater than R. So that way we know that there aren't any ones in the array. Because even if we had one single one, then what would have happened is L would have come to here and R would also have come to here. So since there is not a single one, then L and R would just go on till the end. So that way we'll know that there aren't any ones. So the answer will be just N. Also now in this case, now we have the first element as 0 since we made our array that way. So now the last element must be 1 if this is the else if we are ending up in this condition. So if the first element is 0 and last element is 1, basically we are in this case. And for this case, this would be the answer. So basically you just calculate the number of zeros in front and number of zeros in last and this. And also now number of ones in last. And also if again L becomes greater than R, then the answer would be N, since that would be this case. This case. Basically L would move on to this and R would move on to this. So now L becomes R, that way we know that all the zeros and all the ones are together. So the answer would be N, since we cannot perform any operations. So the time complexity is O of N. This question clear to you guys? You can ask if you have any doubts. So if there is some doubt, you guys can ask. Why did we flip? Basically, if you didn't flip, then you would have to check for all these 4 cases separately. Basically, you will have to put conditions like this. If S of 0 is 0 and S dot back is 0, and you will have to again put condition this if S of 0 is 1 and S dot back is 1. But you will have to put 2 different if conditions, and in this case you will have to count the number of zeros and number in the front and in the back, and in this case again you will have to count the number of ones in the front and ones in the back. So to avoid these 2 if statements, what we can do is we can just flip the whole array for if S of 0 is 1, and if S of 0 is 1 and we have flipped the whole array, then automatically all the ones in the beginning become 0 and the 0 become 1, and all the zeros, all the ones in the end also become zeros, and the zeros become ones. So now we'll only have to count the number of zeros in the front and last. So that way we don't have to put 2 different if conditions. Did you understand, Aditya? You can go ahead and solve the question like this. It would still get easy. This is not wrong, but this is just flipping just reduces the complexity. Actually, 2 cases instead of 4. These 2 cases became one single case, and these 2 cases became again 1. So 0 is 1 and S dot back is 0. Basically, because in this case we were counting the number of zeros in the front and ones in the back. So we are counting this. But if I had gotten this array, what I could have done, I would have flipped all the elements. So it would become something like this. And now again, I would still have to, I would again just do this thing. Calculate the number of zeros in front and calculate the number of ones in back. Since the answer was this only, right? Number of zeros in the start and number of ones in the end, plus one. So that way, okay. So is it clear to everybody now? So I think it is clear to everybody now. And move on to the next question. So the next question is game easy. This is the easy version of the problem, and n is less than or equal to 2000 in this. So you are playing a game on yet another array A of size n. You have k coins at the start, and you'll do the following action. You start with sum equal to 0 and x equal to 0. For each I 1 to n in this order, choose to do exactly one of the following three actions. Do nothing, pay no cost. Do nothing, pay no cost, or update sum as sum plus ai and update x as x plus 1. Or what we could have done is update sum as sum plus ai plus xi and then update x as x plus 1. But this operation costs 1 point and this operation costs 2 points. Your goal is to maximize the final value of sum. Unfortunately, the starting amount of coins is not fixed. Find the answer for each k equal to 1, 2 till 2n. So the constraints are n is less than or equal to 2000 and sum of n over all test case does not exceed 2000. So the expected time complexity would be around k into n or n square, or n to the power 6 can run. Problem C. So in this problem, we are given an array A, and we have two variables. Initially, we have k coins, given an array and k coins. And we also have two variables named sum and x. Sum equal to which are initially 0 and x is also initially 0. So what we can do is process each index of array A in the order 1, 2, 3, 4 till n. And what we can do is basically for an index, either we do nothing or we can do sum plus equal to ai and x plus plus and point minus minus. Either we can do this or we can do sum plus equal to ai plus x and then increase x and reduce coins by 2. We need to tell the maximum value of sum. Maximum value of sum. For k equal to 1, 2, 3, 2n. So since k into n is acceptable in the question, we can try to solve for each k in O of n time complexity. That is one thought, just from the constraints. So let's for now just check out the test cases. First test case is 2, then 1, 2. So we need to solve for k equal to 1, k equal to 2, k equal to 3, k equal to 4. So when k equal to 1, we cannot perform any operation of the second type since we only have 1 point, of the third type since we only have 1 point. So we will just have to do this one operation just a single time. So what we should obviously skip this and buy this. Skip this and add this. So answer in this case would be 2. Now we have a equal to 2. So what we can do is either we can uh do, do let's do it like this, C1 and C2. Let's do it like this. Basically, C1 means the number of operations of this type, C1, and C2 means the number of operations of this type. So if we have 2 points, we can basically perform 0 of this and 1 of this, and else I can perform 1 of this and no, I cannot perform 1 of this and 1 of this, since this costs 2 points. So I can perform 2 of this and 0 of this. So for this case, I'll obviously pick this, and since x would be 0 in the beginning, then I would just get my answer as 2. And if I do this, I can pick both of these and my answer would be 3. So in this case, the answer can be 3. Now we'll solve for k equal to 3. Let's solve here. K equal to 3, C1 and C2. Now C1 can be 3, C2 can be 0, or C1 can be 1, C2 can be 1, or that's it. So basically, if C1 is 3, C1 cannot be 3 actually, because we cannot pick 3, we cannot do this type of operation 3 times. Since there are only at max n operations we can perform like this. So this cannot be done. So that must mean that one observation that we get is C1 is less than equal to n and C2 is less than equal to, because one index only once an operation can be performed on one index. So either we perform this or this. So both must be less than equal to n. So we cannot perform this. So we'll have to do with this, and it doesn't. We need to choose one element. So we can either choose 1 for C1 and 2 for C2. We can do C1 and C2 like this, or C2 and C1 like this. So what happens when we do C1 and C2 like this? We first get 1 and the value of x becomes 1. So the next time when we perform C2 on 2, we get 2 plus 1, since the value of x was 1. So basically we get 4. And if we perform the operations like this, what happens is we get 1 plus 0, since x was 0 in the beginning. And then we get 2. And this would result in 3. So it is better to perform operations in this way only. So that means another observation that we got from here is we perform C2 operations in the end. That is also obvious, because in the end we would have higher values of x. Since in the end, since x can never decrease, in the end we would always have higher values of x. So higher values would be added into our answer. So basically, it's better to perform C2 is in the end. So this was one of this was one, and this was one of the. Now let's move to k equal to 4. For k equal to 4, C1, C2, we can perform 4 of these and 0 of these, or we can perform 2 of these and 2 of these, or we can perform 0 of these and 2 of these. So again, this case would be rejected, since 4 different indices cannot be selected. C1 is greater than C1 is greater than n. This is rejected, and let's check out this. Again, this is also rejected, because another observation that we make here is C1 plus C2 should also be less than equal to n. Since C1 and C2 are uniquely and individually performed on different indices, so the total number of different indices an operation is performed should be less than or equal to n. So we cannot do this as well. This was the third observation, and since we made this observation, we no longer need this. Since this was just a subset of this. So this is now the better condition. Now let's move on to the last case, 2, and uh, we can just do this C2 C2. So the answer would be 1 plus 0 plus 2 plus 1. That would be 3 plus 1 3. So that was the answer. Uh, Basically 2, 3, then 4, and then 4. That was the first test case. Now let's move on to the second test case, also taking note of these two observations. The second test case is 4 1 1 1 4. Now let me write this in. 4 1 1 1 4. So let's now try to solve for k equal to 1. For k equal to 1, what will happen? C1 and C2 would be just like this, 1 and 0. And obviously, we'll skip these and pick this to get the best answer. So answer for this case would be 4. In case of k equal to 2, I can either do 1 0, sorry, 2 0 or 0 1. So again, if I do this, what will happen? I'll just skip these two and pick these two, 4 and 1. So in this case, I'll get my answer as 1 plus 4 equal to 5. And in this case, the maximum answer I'll get is 1 4 plus 0, which is 4. So again, this would be the answer. And for k equal to 3, C1 and C2, what will happen is 1 and 3 and 0, then 1 and 1. I think that's it. So if I perform 3 and 0, then obviously I'll pick the 3 highest numbers, which would be 1 1 1 4. So 1 plus 1 plus 1 plus 4, it will be 7. And if I do one of this and one of this, I'll pick these two, and the answer would be obviously now again C1 and C2 must be performed in this order, because we saw that keeping C2s at the end would give us a better answer. So the answer would be 1 plus 4 plus 1, which is 5 and 6. So this combination gives us better answer. Now let's move on to k equal to 4, C1, C2. We can do 4 0, or we can do 2 1, or we can do 0 2. So if I do 4 0, then simply the answer would be just, oh wait, just a second. Actually, I needed to pick 3 and I picked 4 things. So I can only pick 3. That's pick 3. Just confirm 4 5 6. Yeah. So k equal to 4. If I pick 4 elements, the answer would be 7. If I pick 2 of these and 1 of these, now again I'll use C2s in the end. So I'll use my operations like this: C1, C1, C2, which would give me 1 plus 1 plus 4 plus 2. 1 plus 1 plus 4 plus 2, which is 6 7 8. This 1 plus 1 plus 4 plus 2, which would be 8. 4 plus 2, because x was 0 here, x was 0 here, then x became 1 here, and then x became 2 here. And then if I perform 2 C2 operations, then it would just be 1 plus 4 plus 1. 1 plus 4 plus 1, which is 6. So answer would be in this case 8. And now let's see for k equal to 5. Let me write the test case again over here. 1 1 1 2. For k equal to 5, we can see C1, C2. It can be either 5 0, or can be 3 1, or it can be 1 3 1 2. And that's it. Again, this case will be rejected because of this property. And let's see the answer for this case. I'll perform operations like this C1, 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 C2 to maximize the X in C2. So the answer would be 1 plus 1 plus 1 plus 4 plus 3, which is 10. And in this case, I'll perform my operations like this C1, C2, C2. So the answer would be 1 plus 1 plus 1 plus 4 plus 2. 6, 7, 8, 9. So answer in this case would be 10. 8 and 10. Okay. So moving on to A equal to 6, C1, C2. And then this would be 6, this would be 0, 4, 1, 2, 2, and 0, 3. Let's reject these two possibilities because C1 plus C2 was greater than 4. And now for 2, 2, what I'll have to do is 1, 1, 4, 4, 1, 1, 1, 4. I'll have to use C1 as these like this. So the answer would be 1 plus 1 plus 1 plus 1 plus 4 plus 1 plus 2 actually, and 4 plus 3. So 7, 10, and 12. And in this case, I'll have 1 plus 1 plus 1 plus 4 plus 2. So 6, 7, 8, 9. So answer would be 12. Is 12. A equal to 7. Or we can do C1, C2. Can 7, 0, 5, 1, or 3, 2, 1, and okay. So we reject these possibilities. The case is this, and 1, 1, 1, 4. So I'll have to perform C1, C2, C2, C2. And now the answer in this case would be 1 plus 1 plus 1 plus 1 plus 2 plus 4 plus 3. So 7 and 3, 10 plus 2, 12 plus 1, 13. That will be the answer. Then will be equal to 8 right now. P equal to 8. So this is C1, C2. And 8, 0, 6, 1, 4, 2, 2, 3, and 0, 2. So when these four cannot be used, I have to use this operation, and that will just give me 1, 1 plus 1, and then 1 plus 2, and then 4 plus 3. Same pattern. So that was for the second test case. So now we learned three things from solving these test cases. One was basically, one was this. We perform C2 operations in the end. Let's say there are T1 C1 operations and T2 C2 operations. So what we'll do is perform in these manner. First, we'll perform C1 operation T times, and then we'll perform C2 operations T2 times. So that's how we'll perform. And also C1 plus C2 should be less than N, since obviously we cannot pick more than N. And one more thing, since for given C1 and C2, we'll have to pick C1 plus C2 elements from the array. We will obviously pick the highest, maximum C1 plus C2 in the array. Basically, we must pick, write the three observations here again. First, we will perform C2 operations in the end. Second is C1 plus C2 must be less than equal to N. And then another observation is we will use the highest elements Basically, what I mean by this is, if I have an array like 1, 3, let's say 7, 5, 2, 9, uh, 4, and then 11. So if I am solving for this configuration, C1 equal to 2 and C2 equal to 3, I need to pick 5 elements, right? So instead of just randomly picking any 5, I'll pick this, and this, since they are the highest 5. So I'll give them this order, so that now the values of x's would be the maximum. Values of x would be the maximum that we add in the sum. So we'll use the highest elements. This is the third property. Now using these properties, we can now formulate what we were doing above. We were basically, what we were doing is picking C1 plus C2 elements, C1 plus C2 highest elements. So our answer would be sum of C1 plus C2 highest elements and what else? Basically, we'll perform the operations in this manner, right? C1, 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 and then we'll perform C2, C2, C2. So here the value of x would be, let's say T1, which is the number of C1s we perform. Number of C1s. Number of C1s. And here the value would become T1 plus 1, and till the end it would become T1 plus 1 plus T1 plus T2 minus 1. So basically, our total answer would become sum of these C1 plus C2 highest elements plus sum of these x's, values of x. So sum of C1 plus C2 highest plus T1 plus T1 plus 1 plus T1 plus T2 minus 1 till T1 plus T2 minus 1. So this becomes simply, since these are T2 elements, so what I can do is make this T2 into T1 and then plus 0 plus 1 plus 2 till T2 minus 1. And the sum of this, we know it's T2 into T1 plus, we know this sum, since sum of 1 plus 2 plus 3 till n is n into n plus 1 by 2 using the formula of AP. Number of elements by 2 into first plus last. So number of elements here we have total T2 elements. So T2 into first plus last, T2 minus 1 upon 2. So this was the extra sum of C1. So our answer would be this plus sum of C1 plus C2 highest elements. Right. So now I can find the best possible answer for a given C1 and C2 configuration, where C1s, there are T1 C1s and T2 C2s. So what I can do is for each k, since I know that C1 plus C2 is less than equal to n, so for each k, what I can do is brute force over C1. Force over C1s. So what this is basically, I'll have C1 and then I need to find the number of C2s. So what would be the number of C2s? Basically, K minus C1 would be the leftover points, and dividing this by 2 would give us C2. So that way we can find C2. and for every C1 we can find the C2. Now C1 plus C2 should be less than equal to n, right? So if so C2 can be maximum of n. So C2 must be maximum of n, actually minimum of n comma this. For because k minus C1 by 2 uh, might exceed the maximum value of C. So this is basically the solution. Now I'll show you guys the code for this, and then I'll explain it later in the action. So basically, what I did is I took the input and then sorted and then reversed. So what this would do is basically give me the highest elements in the array in the starting, and then I took prefix sum so that I can do this in O of 1, perform this in O of 1, perform this in O of 1. Since I can just use prefix sum to calculate the sum of C1 plus C2 highest elements. So I took the prefix sum. So now V holds the prefix sum. And since I need to calculate for k equal to 1 to 2n, I'll calculate for k equal to 1 to 2n. And now what I'll do is take just a second. Take is actually C1 plus C2. Take is C1 plus C2. So the number of elements that I am taking is take, and also current would be storing the answer for a given C1 plus C2. And if take is greater than k, then continue, because I cannot take more than k, because then the number of C2s, because C1 plus I have only k coins, right? I have only k coins, and if I take more than k elements, then that would cost me more than k coins, because if I take k plus 1 elements, that costs me k plus 1 coins, minimum k plus 1 coins, assuming that I'm only performing C1 type of operations. So I can take at max k. So another thing is C1 plus C2 should be basically take should be less than k, less than or equal to k. I cannot take more than k. So if take is greater than k, I just continue, because that case I do not care. Now current would be just the sum of all the highest take elements, that is C1 plus C2 elements, and left is basically the coins I have been left after choosing all the operations as C1. So basically what, let's say I have take equal to 5, and I had k equal to 10 coins. So no, 10 is a little more. I'll take 8 coins. Okay. So if I had k equal to 8 coins and take equal to 5, what does that mean? Basically, I'll first do like this: C1, 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 C1. I'll do all the 5 operations as C1s, and now I have 3 leftover coins. I have 3 leftover coins now, so I can make these 3 as C2s. C1, C1, C2, C2, C2. So I know that I'll have 3 C2s, because each leftover coin can now convert one C1 into C2. So basically left means the number of C1s that will be converted into C2, and then in current I just add the total value that will come from these C2s, which is basically whatever x was here, x plus 1, x plus 2, sum of this. And I just take answer equal to max of answer comma current, see out answer would give me the answer. So that was the code. What we did is 2n into n, 2n square. And now if anyone has any doubts, they can ask. Explain the take part. Okay. Uh, Basically what I'm doing is, let's say take equal to C1 plus C2, right? Now what I'm doing is iterating over this take value, iterating over this, and obviously to maximize my answer for a certain take value, I need to maximize the number of C2s in it. I need to put as many C2s as I can, because C2 gives me additional score. C2 gives me that plus X as well. So I need to maximize the number of C2s in my take. So what I can do is, if I have K equal to 10 coins and take is equal to 5, so basically I can do 5 C2s. If I had take is equal to 6, what I could have done is 2 C1 and 4 C2s. Because I have to take 6 elements, and if I'm taking 6 elements, I'll maximize the number of elements that I'm taking as C2. If I have take equal to 7, then I'll take basically 3 coins are left. So 7, and then I can 4 C1 and 3 C2. Sorry, 4 plus 3. Okay, I can do this. I'll make all of them as C1, and then I have 3 leftover coins. So yes, 4 C1 and 3 C2. This would be for take equal to 7. For take equal to 8, I'll have 8 and then 2. So 6 C1 and 2 C2s. This would be the best combination of C1 and C2 for a given sum. Since I maximized C2s. If I increase the C2s any further, I would the total sum would not be equal to 6. Because if I take 5 C2s, then I cannot take 1 C1, since then the sum would be 11 coins. So I am basically distributing each take as maximum number of C2s. Did you understand that, Arnav? Okay. So basically, and now for this configuration, we know what the most optimal answer is. So we can just calculate this V of, basically in the prefix sum, we just take prefix sum of take plus this left into take, left into take. Left is number of C2s minus left into left plus 1 by 2. And how did we get this part? This part is nothing but just since I had C1 plus C2 total, right? So what we'll do the operations like this. Sorry, C1, 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 and then C2, C2. So the value of X here would be C1 plus C2 minus 1 before performing this operation. So it would be take minus 1. So if I am performing C2 here, then I would be adding take minus 1 in my answer. Or when I performed here, I would be adding take minus 2 in my answer. So I'll be adding like this, take minus 1 plus take minus 2 till take minus left, because left is the number of C2s. So this would just be take into left into plus minus, actually minus left into left plus 1 upon 2. Again, the formula we calculated above, I think, was a little different than this, but it would give the same answer. Wait, what did I do wrong here? T1. This would be T1 plus T2 minus 1. And then we subtract 1 for T2 times. So this is actually T1 minus 1. Okay. T1 minus 1 and then T1. So that was where I was wrong here. So T1 plus T1 plus T1. Actually, not this. It would be something like T1 minus 1 plus T1 plus T1 plus 1 and then till T1 plus T2 minus. And some of this we can do it like this, T1 into T2 plus minus 1 plus 0 plus 1 till T2 minus 1. And this is nothing but total elements upon 2 into first plus last, which would be T2 minus 2 minus F plus 1. Wait, what? That should be coming same. I must be doing some wrong calculation. They are performing like this, and there are T1 of these. So the score here must be T1. Okay, sorry, not T1 minus 1, and T1 plus 1 till T1 plus T2. And the total sum of these extra scores would be T1 into T2 plus 1. Okay, no, T1 plus T2 minus 1 here. Actually, okay, sorry. So this would be T1 into T2 plus 1 plus 2 till T2 minus 1. So T1 into T2 plus this is T2 into T2 minus 1 upon 2. And since take was T1 plus T2, and this is T2. Okay, so T1 into T2 plus T2 into T2 upon 2 minus T2 upon 2. Take into left, right. So I can take T2 common from, I can split this as T1 into T2 upon 2 plus T1 into T2 upon 2 plus this is T2 into T2 upon 2 minus T2 upon 2. This becomes T, I take T2 by 2 common and then T1 plus T2. And from these two terms, I can take T2 common. So T2 by 2 into T1 minus 1. So this is nothing but left into take, and T2 is left. I'm doing some wrong calculation. Yes. T2 into T2 minus T2 into T1 into T2. N into N plus 1 upon 2. So T2 minus T2 upon 2. And this is T1 plus T2 square minus T2 square upon 2 minus T2 upon 2. So T1 T2 minus T2 square upon 2 minus T2 upon 2. And this is T1 T2 plus T2 square upon 2 minus T2 by 2. By plus T2 square minus T2 take -1, take -2, and take minus left. So, okay. This is take -1, and this must be T1 -1. Yeah, I think I did this part a little wrong. So, reflection of take. Let me just do it one last time. C1, C2, C1, 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 and then C2, C2, C2. So total is take. So I must have the value of take -1 at this point, and before it take -2. And here I must have take minus whatever the left, take minus T2 basically. So this would be take minus left plus take minus left plus 1 till take -1. And since there are total left terms, this is -1, -2, -3 till minus left. So I can take into left and simply minus of 1 plus 2 plus 3 till take. And this would be take into left minus of, sorry, left, left into left plus 1 upon 2. So that this should be the formula. I don't know what kind of mistake I can't find a mistake right now in that. But yeah, this is the formula. In any way, if you solve this sequence, it should give the same formula. So did you understand? I'm sorry, I confused you a little bit there, I think. Okay. So basically now I got this was my extra, and the prefix sum of take, that would be adding the AI values in the sum, and prefix sum of take plus this extra would be the maximum value for a given take value. So I can just find the maximum over all these, and that would be the answer for that take. So this was it for the question. I don't think you guys have any more doubts, so let's move on to the next. So problem D is same as the last problem, but here now n is less than equal to 2 into 10 to the power 5. So now we cannot do O of n for each k. So we'll have to basically optimize finding the maximum of this function. In the last case, we were finding the maximum of just like problem E. So in problem D, we found the maximum of this function. Prefix sum of take plus take into left minus left into left plus 1 upon 2 minus left into left plus 1 upon 2. So we maximize this function for each take value, where the value of left is equal to k minus take. Basically, k was the number of points and c is the number of elements we are doing operations on. So left will be the number of C2s that. So we're trying to maximize this function and we just brute forced over all values of take, but we cannot do that anymore. So let's try to figure out what's the maximum of this function. So let's just put the value of left and make this a function of take. So take plus this is take into left. So take into k minus take minus left plus k minus take and k minus take plus 1. That is fx of take plus k into take minus take square minus k square plus take square minus 2 into k into take. That is of k plus if I open this, I have a into take and plus 2k into take, so that will become 3k into take. Okay, another 2 I need to multiply here. So that actually becomes 4k into take and minus 2 take square minus take square minus 3 take square and minus k square plus 2k plus sorry, I've taken this element. Okay, I missed some here k square plus take square minus 2k into take, that is into this plus k minus take also. So minus k square plus k minus take upon 2 prefix of take plus this is minus 3 take square plus I take common 4k minus 1 and minus k square plus k upon 2. So I need to maximize this function for each and every value of take. So what I know is this is an increasing function always, since this is prefix sum. So the graph of this function must look like this. And and the value of this is a quadratic with this value as negative. So the graph of this quadratic must look something like this. So if I add these two functions, it might not be a quadratic, but it would still have some maxima like this, because this function is increasing and this is also increasing in the start. So this will increase with this, and this is also increasing. But now this function starts to decrease, and since this is quadratic, this would have more slope of decreasing. So it would like the maxima due to this would die down soon. So what we can do is, to find the maximum of this type of function, we can use ternary search. If we had to only find the maximum of this part, we could just use the maximum of a quadratic function as minus b by 2. But since this is not a quadratic anymore, we need to find ternary. We need to use ternary search to find the maximum. And I'll explain a little about ternary search. So what is ternary search? Basically, if I have a function like this and I need to find this maximum point, and I know it lies between this L and R. L and R in this case would be the maximum minimum value of take, one take n. So what I can do is I take these 2 points, M1 and M2. Basically, these 3 parts, I actually divide them in equal parts. This this and this. So these three parts are equal, and I take the points M1 and M2 here. So what happens is M1 is here and M2 is here. So if the value of M1 is greater than the value of M2, we know that the maxima cannot be in this region. So we can move our R upwards. And if the value of L is less than, if the value of, if the M1 and M2 came out to be like this, just came out to be like this, M1, M2, then we know that the maxima cannot be in this region. So we move the value of L here. And that way we decrease our search space and uh, converge to this point. And this, the complexity of this would be log 3 base n. Since in one step we decrease our search space by L by total search space by 3. Since we divide in 3 equal parts, hence it if the search space must be reduced by this or it must be reduced by this. So in each step it is getting reduced by a factor of 3. So basically, in the first step, if our search space was this, in the next step it becomes 2 into 2 by 3, and then in the next step it becomes 4 by 9. So 4 by 9. So that way it will take at max log 3, log base 3 of n steps to converge on a fixed value. So I'll show the code. It was same here. And the function I'm performing ternary search on, it's exactly same as the last part, last question. And simply what I'm doing is finding the M1 and M2, which is L plus total search space by 3 and R minus total search space by 3. And if M2's value was greater than M1, then I can shift L or I'll shift R, and I do this till they converge up to till a certain point, and then I can just brute force for 3 or 4 values and check the maximum value of answer, and that will be the answer. So that was for the E question. D question. Anyone has any doubts, they can ask. So I'm talking about. So now I'm